Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to lesson 19. 4 interesting transformations of functions. Classwork. Exploratory challenge. Let f of x equal x squared and g of x equal f of 2x, f of 2x, where x can be any real number. Write a formula for g in terms of x squared, i.e. without using f of x notation. So f of x is x squared. F of 2x, so what you're going to do is simply take this 2x, substitute it in place of this x, and then say g of x equals f of 2 of that, and f of 2x will now replace x here. So it's kind of like a substitution full circle type thing. So I'm going to say g of x equals, and I want it to say f of 2x, but not using the f of x function. So f of x equals x squared, so f of 2x, let me explain that, f of x equals x squared. That means whatever you put in here gets put in here. So f of 2x would equal 2x squared. So g of x is now going to equal f of 2x, and that is 2x squared, and it's the quantity 2x squared. So that 2 gets squared as well when you distribute. So it would equal that, or if you distributed before x squared without the parentheses. Now it says to complete the table of values for these functions. So if f of x equals x squared, so all we're going to do is take x and square it. So negative 3 squared is a positive 9. Be careful whenever you square you get a positive, because a negative times a negative is positive. Negative 2 squared is 4. Negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. G of x equals f of 2x. So now we're going to take f of 2x, so it's going to be 2x squared. So basically what we're going to do is be squaring 2 times this x. So at first, if you feel more comfortable doing one step at a time, it'd be negative 3 times 2, which would be negative 6. Negative 2 times 2, which is negative 4. Negative 1 times 2, which is negative 2. 0 times 2 is 0. 2 times 1 is 2. 2 times 2 is 4. And 2 times 3 is 6. And now we're going to square those, because f of 2x means take this, double it, and take f of x, and that means squaring these numbers over here that are green. So negative 6 squared is 36, negative 4 squared is 16, negative 2 squared is 4, 0 squared is 0, 2 squared is 4, 4 squared is 16, and 6 squared is 36. Part C says graph both equations, y equals f of x and y equals f of 2x. So if I graph this, it's the point negative 3, 9. So notice this is 1/2, 1, negative, or I should say negative 1/2, negative 1, negative 1.5, negative 2, negative 2.5, negative 3. And my first point is negative 3, 9. So it's negative 3, and it's up to 9. So it's off the grid, so I can't graph that here. Then I do negative 2, 4 is here. Negative 1, 1 is right here. We're going in 0.5 is our unit of measurement. Negative 1, 1 is what I just graphed. 0, 0 is the origin. 1, 1 is right here. 2, 4. And then 3, 9 would be off the grid. So then when I plot these and then I graph them, I draw a line through here. Bear with me, this is really difficult with this writing pad. But it's going to come down, curve, and come back up, and it's going to continue off the graph forever, and it's going to continue off the graph forever, like so. So there's an approximation. Again, very difficult to draw with this pen. Okay, so now we're going to graph these. Well, 36 is way more than 6. 16 is way more than 6. So I can only start graphing here to here. I can only graph these 3 points. So it's negative 1 comma 4. So negative 1, 4 is here. 0, 0, 1, 4. And then we graph. Like so. Okay, that would curve around a little bit better than that, like so. And there is our 2 graphs. Okay, page 2 brings us to part D. How does the graph of y equals g of x relate to the graph of y equals f of x? Okay, so I brought in a better graph. So y equals f of x is the red parabola. And y equals g of x is the same as y equals f of 2x. That is g of x, that's the blue one. So how do these 2 graphs relate to each other? So how does g of x relate to f of x, which was the parent function? Okay, the corresponding x values of y equals g of x is half of the corresponding x value of y equals f of x. When g of x equals f of x, the point of the graph of g are 1/2 the distance to the y-axis as the corresponding points of the graph of f, which makes the graph of g appear to shrink horizontally. Okay, so what they're trying to say is to get from the origin to this point on y equals f of x, let me switch to pen. So if I go from here to here, what we're doing is, the first thing we're doing is we're going over 2 units and then up 3. But in the other function, we went over 1 unit. Did I say over 2? Yeah, over 2 units, up 3. Now we're only going over 1 unit and up 4. And I said up 3. That's because I'm watching the steps. So step 1 means go from 0 to 2. Step 2 says to go from 2 to 3. And to get to that same y value on g of x, we have to go half the distance we went. So this is a distance of 2, and this is a distance back of 1. And that's what they mean by half the corresponding x value of y equals f of x. So the x value that corresponds to this y value of 4, the x value on f of x is 2, and the corresponding x value on g of x is 1, which is 1/2 of 2. Okay. Part E says, how are the values of f related to the values of g? Okay, for equal outputs of f and g, the input of g only has to be half as big as the input of f. The only time they're going to be the same is when we're at 0, because half of 0 is still 0. Okay, exploratory challenge 2. Let f of x equal x squared and h of x equal f of 1/2 x, where x can be any real number. Rewrite the formula for h in terms of x squared. In other words, don't use f of x. Okay, so h of x equals f of 1/2 x. So what we're going to do is take this 1/2 x and we're going to put it right here. And when you do that, you also put it right here. So f of 1/2 x will equal that x squared, or this squared. So in other words, h of x equals 1/2 x squared. Okay, now it says to complete the table of values for these functions. So again, it's going to be the same as the last one, so I'm just going to go through this quickly. -3 squared, 9, -2 squared, -1 squared, 0 squared, 1 squared, 2 squared, 3 squared. Alright, so now what we're going to do is take 1/2 of x and square it. So I'm going to do halves over here, so I'm going to do a column with 1/2 x. Just so you see where these values are coming from. 1/2 of -3 is -1.5. 1/2 of -2, 1/2 of -1, 1/2 of 0, 1/2 of 1, 1/2 of 2, 1/2 of 3. Now we're going to take those and square them. F of 1/2 x. So we're going to take half of the x and square it. 1/2 of 1.5. 15 squared is 225. So that'd be 2.25, and it's always going to be positive because a negative times a negative is positive. So 2.25. Negative 1 squared is 1. 0.5 squared is 0.25. 0.25. 0 squared. 0.5 squared. 1 squared, and then 1.5 squared is 2.25. So there are our table of values. Okay, page 3 brings us to part C. Graph both equations y equals f of x and y equals f of 1/2 x. So I brought in the table just so it'd be quicker, and then switching back and forth from page to page. Negative 3, 9 will not go on this graph because it only goes up to 6. Negative 2, 4 is right here. Negative 1, 1 is right here. Keep in mind that our unit of measures is 1/2 unit every square. 0, 0 is the origin, which is here. And then 1, 1 is over 1 up 1. 2, 4 is over 2 up 4. And 3, 9 is off the grid. So then I'm going to connect these dots. So I'm going to come down and curve around as neatly as I possibly can with this pen tool. It's very difficult. And that continues up like so, and that continues up like so. This isn't quite that steep. It would be more here. All right. All right, that's a little better. But anyway, you get the idea. Going through this point right here and this point right here. Okay, now we'll do the blue one. Negative 2, comma 1. Negative 2, 1 is right here. 0, 0. I skipped negative 1, 1. So negative 1, 1 is here. No, it's not. Just kidding. I don't want negative 1, 1. That's the other one. Negative 1, 1/4. So this is negative 1, 1. This is negative 1, 1/2. This is negative 1, 1/4. Right down there. Okay, that's better. All right, so then 0, 0 is already there. And then over 1 up 1/4. 1, 1/4. 2, 1 is here. And then 3, 2 1/4. And I didn't do negative 3, 2 1/4. I can do that. I was looking at the y value from f of x again. So there we go. All right, so this is going to come up like so. And it's going to continue over like this, opening up slower. It's wider. And then this one is going to come up like this and continue like that. So there is the parabola here, and there's the original f of x, and this is h of x. F of x. How does the graph y equals f of x relate to the graph of y equals h of x? Okay, so how are they related? So I'll bring this in. And it says, since the corresponding x values of y equals h of x. So now they're taking a corresponding x value. So how about 2, 2, 1, and 2, 4. That's a corresponding x value. Since the corresponding x value of y equals h of x, corresponding x value of y equals h of x, is twice the corresponding x value of y equals f of x when h of x equals f of x. Okay, so what they're saying here is they are, let me get that out of the way and delete it. They're comparing h values, or y values, I'm sorry. So h of x is y, so y equals y, if you will, yes. H of x is y, f of x is y. So we want the same y value. So this is the point 1, 1. So now let's go back and say, since the corresponding x value of y equals h of x, this x value here is twice the x value of y equals f of x, when h of x equals f of x, in other words, when they're both equal to 1, when y is 1, The x value in f of x is 1/2 of the x value of h of x, or h of x is 2 times the distance to the y-axis. So how far is it from here to here? 1. How far is it from here over to here? 2. So h of x is twice as far away from the y-axis as f of x. So it appears to stretch horizontally. E says, how are the values of f related to the value of h? Okay, to get equal outputs of each function, the input h has to be twice the input of f. So in other words, looking at another point, if I want to get to the point 4, so I will draw a horizontal line at 4. If I want to get to this value of the function, in f of x, I'm at 2. In h of x, I'm at 4. So my graph isn't drawn that well. This should have gone up a little steeper and come through here. Okay, and same with over here, it should be -4. So that was opening too slow. So that's my actual graph over here. So let me just fix that for you. Okay. So it's more like that, and it's going through this point here. So this is a distance of 2, but this is a distance of 4 when the y values of each function are 4. All right, exercise. Complete the table of values for the given function. Okay. Now we have f of x equals 2 to the power of x. So I'm going to take -2 and put it up here. So 2 to the -2 equals 1/2 to the +2. If you don't recall the rules of exponents from Math 8, so the -2 tells us to take the base and take its reciprocal, because that is 2/1. So you flip it and change the sign to positive, and 1/2 squared, then you distribute. 1 squared is 1, and 2 squared is 4. So that's 1/4. Okay, so then if I did the same here, -1, you might want to do this on the side and write it out. So -1 is our power, not our base. So it's 2 to the -1, which is 1/2 to the 1, which is 1/2. Okay, 2 to the 0 equals 1. Anything to the 0 power is 1. 2 to the 1 is 2, and then 2 squared is 4. Okay, so there's our first column. Let me get this out of the way, and then move on to G. Now it's 2 to the 2x, so we're going to take G of x equals 2 to the 2x. So that's going to be 2 to the power of -2. Actually, let's put it in the same order. 2 to the 2x. So that'd be 2 to the 2, x is -2 this time. So that'd be the same as 2 to the -4, which would be 2, or 1/2. I'm sorry, I'm supposed to erase that there. And think of that as 2/1 to the -4. So it's going to be 1/2 to the 4th, which is 1 to the 4th, which is 1, and 2 to the 4th, which is 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is 1/16. Okay, now we're just going to do this again, and our x is now -1. So it's 2 to the 2x, or 2 times 2 to the x is -1, so that'd be 2 to the -2, which is 1/2 squared, and that's 1/4. Okay, and then continuing this way, let's erase that. And now I have two to the 2, and x is 0. Well, 2 times 0 is 0, so this will end up being 2 to the 0, which is 1. And then the next one, we're switching our 0 here to 1. So this is 2 to the 2 times 1, which is 2. 2 squared is 4. And then the last one, we're just going to change this to a 2. And that would be 2 times 2, or 4. And 2 to the 4th power is, as we said earlier, 1/16. I'm sorry, just 16. There's no fraction here because it wasn't negative. All right, so 2 to the 4th power is 16. Okay, moving on to this one. I'll do that over here. H of x equals 2 to the power of negative x. So this is going to be 2 to the power of negative 2, which is positive 2. 2 squared is 4. And then this one would be 2 to the negative 1, or 2 to the 1, so that's 2. 2 to the negative 0 is just 2 to the 0, that's 1. 2 to the negative 1, for this one, 2 to the negative 1 equals 1/2 to the positive 1, which is simply 1/2. And then finally, 2 to the negative 2 equals 1/2 to the positive 2, which is 1/4. Okay, put that 4 back, 1/4. So there is our table of values. Okay, page 4 brings us to part B. It says to label each of the graphs with the appropriate functions from the table. So if you see here, notice here that they're all crossing right here at the point 0, 1. And that is right here, 0, 1, 0, 1, 0, 1. So this point here is not helpful to us in determining which function goes where. And again, our y values are over here, and we have a 16 here, and that was when x was 2. So that's first thing I would look at is go over to 2, which is here, and go up 16, and there's the point 216 right there. So this is g of x. And then check other points. Here is the point 1.58, but that's not on our grid. So if I check this point 1, 4, then I should go over 1 and up 1, 2, 3, 4, and that is right here. So this point here is on g of x. This point's on g of x. 0, 1 would be right here, and negative 1/4 is right here, and negative 2 1/16 is right there. So that is definitely g of x. Okay, so let's erase all of this. All right, so now we're going to look at the point 2, 4. Where is 2, 4? Here's 2. Here's 4. The point 2, 4 is right here. The point 0, 1 is right here. The point 1, 2 is over 1 up 2. That's right here. 1, 2, 3, 4 is here. 2, 4 is there. I marked that wrong. That's 2, 4. And negative 1, 1/2 is right here. And negative 2/4 is right here. So this is f of x. All right, so then finally by elimination, but we still want to make sure we're correct, we're going to check, so I'll mark these in red. So if I go to the right 1/16, I'm sorry, negative 2, go to the left 2, up 4. 1, 2, 1, 2, 3, 4 is right here. Left 1, up 2, left 1, up 2. We're on that point. 0, 1, again, everybody shares this point. And then 1, 1/2, 1, up 1/2 is right there. And 2/4, over 2, up 1/4. So the red one is h of x. Okay, part C says, describe the transformation that takes the graph of y equals f of x to g of x. So in other words, what made this blue graph get to g of x, which is purple? What did we have to do? Okay, the graph of y equals g of x is a horizontal scale with a scale factor half of the graph of y equals f of x. So they're saying we're only half the distance from the y-axis. So this point right here at 16, in f of x, the x was 4. And in g of x, the x is 2, which is half the distance from y, the y-axis. Okay, half of the graph. Scale factor 1/2 of the graph of f of x. D says consider y equals f of x, the blue one, and y equals h of x, the red one. What does negating the input do to the graph of f of x? So what did negating the exponent do to f of x to get it to h of x? Okay, the graph of h of x is a reflection over the y-axis of the graph of f. So every point that's on this blue line, if you go over to the y-axis like this one, go over one more, you're at h of x. Go over 2 more, you're at h of x. Up here, 1, 2, 3, 4 units from the y-axis. 1, 2, 3, 4 units from the y-axis. So this is a reflection about the y-axis. E, write the formula of an exponential function whose graph would be a horizontal stretch relative to the graph of g. Okay, a horizontal stretch. Okay, answers will vary here. There are many different possible outcomes, but here's one of them. We could say y equals 2 to the power of 0.5x. Okay, so what are they talking about? Horizontal stretch. So if you make the multiple of the exponent a fraction less than 1, it would be a horizontal stretch. It would make it grow slower. Okay, page 5 brings us to exploratory challenge 3, and it says, look at the graph of y equals f of x for the function f of x equals x squared. And exploratory challenge 1 again. Would we see a difference in the graph of y equals g of x if -2 were used as a scale factor instead of 2? If so, describe the difference. If not, explain why not. Okay, so here's the graph they're talking about. F of x is the red one. That is the function x squared. Would you see a difference in the graph of y equals g of x if -2 were used as a scale factor instead of 2? If so, describe the difference. If not, explain why not. Okay, so it says there would be no difference. The function involves squaring the value within the parentheses. So both the graph of y equals f of 2x and the graph of y equals f of -2x are the same set as the graph of y equals g of x, but both correspond to different transformations. The first is a horizontal scaling with a scale factor of 1/2, and the second is a horizontal scaling with a scale factor of 1/2 and a reflection across the y-axis, but it would not be visible. So let me explain that a little bit. Let's pick a point on f of x. How about right here? This is the point 2, 4. So what they're saying is if we took and said f of 2x, it would grow twice as fast, and it would, let me use purple. So if I chose 0, 2 times 0 is 0, so that'd still be here. And then if I went over to 1, it wouldn't be up at 1, it'd be 2 times 1 now, it would be 2, and so it would grow faster. So if we had an x and a y, and this is f of 2x, and we put 0, and then f of 2x, well, that's the same as saying 2x squared. So 2 times 0 is 0, 0 squared is 0, 2 times 1 is 2, times 2 is 4, so I'd go over to 1 and up 4. Okay, so then if I plugged in a negative 1, it'd be 2 times negative 1, or negative 2 squared, which is positive 4 as well, negative 1 up 4. And so then it would be a parabola that comes down like so, very steep, curving back around and coming up like this. Okay, I'm off a little there, but you get the idea. So what they're saying is, if you change this to a negative 2 here, what would that do to these values? So now if I plugged in 0 here, and not this one, but this one up here, negative 2 times 0 is 0. 0 squared is still 0. We're at this point right here. Plug in 1, it's going to be negative 2 times 1, which is negative 2. Negative 2 squared is positive 4. So we're still at the point 1, 4. And then negative 1, quantity squared, or negative 1 times negative 2 is positive 2. 2 squared is 4. So at negative 1, we go up 4, and we're at this point again. So we're going to get the same graph if we're doing f of 2x or f of negative 2x, because squaring a positive and a negative gives us the same value. A negative 1 squared gave us 4, and when we plugged in a 1, squaring that gave us 4. Okay, part B says, a reflection across the y-axis takes the graph of y equals f of x for the function f of x equals x squared back to itself. Such a transformation is called a reflection symmetry. What is the equation for the graph of the reflection symmetry of the graph of y equals f of x? Okay, so what they're saying is, if you take x squared, and it's a parabola, and it's crossing the y-axis like this, and you reflect it, well, now this point is going to be here, this point is going to be over here, this point's going to be over here, and this point's going to be over here, and the origin stays where it is. So just picture this thing rotating 180 degrees and landing on top of itself. Not rotating 180, but reflecting across the y-axis, if you will. And all of these points over here will end up on the right, and all the points on the right will end up on the left. So they're asking, what would be that function? So if we have the function y equals f of x, then its reflection would be y equals f of negative x. And that would reflect it across the y-axis. Part C says, deriving the answer to the following question is fairly sophisticated. Do this only if you have time. In lessons 17 and 18, we used a function f of x equals the absolute value of x. Examine the graphical effects of the transformations of a function. In this lesson, we used the function f of x equals x squared to examine the graphical effects of a transformation of a function. Based on the observations you made while graphing, why would using f of x equals x squared be a better option than using the function f of x equals the absolute value of x? Okay, so not all of the effects of multiplying the input of a function are as visible with an absolute function as they are with a quadratic function. For example, the graph of y equals 2 times the absolute value of x is the same as y equals the absolute value of 2x. Therefore, it's easier to see the effect of multiplying a value to the input of a function by using a quadratic function than it is by using the absolute value function. Because it's not the same if it's negative. If you move that 2 inside here and you have an x squared, y equals 2x squared, and then you change that to y equals 2x squared, it's easier to see the effects of multiplying a value to the input of a function by using quadratic rather than by using the absolute value. So in this case here, these are not equal, as they this is equal. So I brought my calculator out just to show you this. So I went to y equals, and this is 2 times the absolute value of x, and this one down here is the absolute value of 2x. And you see this little circle I put over here? I did that by coming over here and just pressing enter until I got that circle. That's just a little thing that traces as it goes. So then when I graph these, there's 2 absolute value x, and there's absolute value of 2x. So as you see, it traces right over top of the other one. They're identical. But if I come to this equation here, 2 times x squared is not the same as 2x squared. I can't just simply move this 2 in here, because now that it's inside the parentheses, this is equivalent to 4x squared without parentheses. I didn't mean to write the parentheses. So if I distribute this 2, this exponent 2 to both, 2 squared is 4, x squared is x squared. So 2 times x squared is not the same as 4x squared. And so if I graph that, let me clear these. So if I put 2 parentheses x squared, let me try that again. Delete, there, no, and just put a 2, I guess. Okay, so there's 2x squared, and then if I put parentheses and put the 2x on the inside and square it, there, I meant to do that. So now we just move the 2 inside like they did here, and as you saw when I graphed that, these are the same function when they're graphed, but what's going to happen when I graph these parabolas? Are they going to land right on top of each other? There's one, and there's the other. No, it's steeper because it's 4x squared, because when you move the 2 inside, it's also getting squared. So these are not equal functions. So the effects of the quadratic will be seen there where they were not in the absolute value function. Page 6 brings us to the end of lesson 19. Go to your problem set.